Thanks for your attention. It's an honor to represent Class 6 here. It's also quite a challenge. Nobody else has mentioned the challenge aspect of this, but I think it really is quite a challenge to talk to this kind of audience. I'm an economist, and I'm going to talk to you about climate change. Probably quite an appropriate thing to be talking about on a day like this when the temperature outside is 90 degrees plus and it's in April. I thought I would start off with a summary of the points that I'm going to make. Just a very quick summary, and then I'll come back over each of them in more detail. So we want to limit climate change, limit the increase in temperature by reducing the emissions of greenhouse gases. I think everybody knows that. Greenhouse gases, again, everybody knows, come from fossil fuels, which are used primarily, but not exclusively, for generating electricity and in transportation. So we have to replace fossil fuels in generating power and in transport. We have lots of technologies which will let us do this. It's technically perfectly feasible, but it will cost. There's a cost associated with it. The cost actually is quite small. The cost, I'm going to argue, is around about 0.2% of gross domestic product annually. So that's 37.6 billion this year. But you divide that by the population of the United States, it comes to $125 per person per year. $125 per person per year you can think of as roughly the cost of one cup of coffee at Starbucks every 10 days. So that's what it would cost you personally to massively reduce the emissions of greenhouse gases here in the United States. So where do these greenhouse gases come from? So this gives you a breakdown. The biggest single source is power generation, but almost the same level of greenhouse gases comes from transportation as well. Those are the two biggest sources. Industry, meaning basically process heating of one sort or another fifth, and then sort of space heating. Commercial and residential means space heating, water heating, and things of that sort. I'm going to focus on electricity generation and transportation because those are the biggest sources, and that's really all I've got time for in 15 minutes. So there's a lot of time pressure on us here. There's a scientific consensus that an increase in temperature of more than 2 degrees is dangerous. And if we're going to keep the temperature increase to 2 degrees or less, that means a really massive reduction in greenhouse gas emissions by the middle of this century. So the cost of mitigating climate change, avoiding climate change, which is what I want to talk about, is really the cost of replacing fossil fuels. The question is, what does it cost us to replace fossil fuels? What does it cost us to replace them in power generation, where we use basically coal and gas and a small amount of oil? And what does it cost us to replace them in transportation, where we use gasoline, jet fuel, diesel, and bunker oil? Bunker oil, in case you wonder what that is what's used in large ships. So let's talk first about the options for replacing fossil fuels in power generation. So we can use wind, we can use solar. There's two forms of solar photovoltaic, solar thermal. We could use nuclear, we could use geothermal, we can use hydro. There's a variety of other technologies which can generate power without generating greenhouse gases. Can we actually adopt these options? Can we, in fact, replace coal and gas by wind or by solar or by nuclear? So technically, the answer is absolutely yes. We can produce way more energy than we need by any one of these sources. For example, we could produce all the power we need from solar. We could produce all the power we need from wind, or obviously from nuclear. However, the issue we have to focus on a little bit here is that while wind and solar are certainly feasible options, they don't produce power all of the time everywhere. They are, in some sense, site-specific. So, for example, solar power is great in deserts, but it's not very good in Scandinavia, where the sun doesn't shine for half the year. Wind is very good on high plains, but it's not good in deep valleys, where the wind doesn't blow so much. That has some implications. It means that if we're going to rely on things like solar and wind, we need a very well-integrated power grid, because it means that we're going to be generating power in certain places where the sun is shining, where the wind is blowing, but typically consuming it in other places. So we have to move the power around a great deal. At the moment, we don't have great capacity to do that. The US electric grid is not particularly well integrated. So we need to improve the integration of the grid a great deal. A lot of infrastructure investment there. The other issue we have to worry about a little bit is that, of course, solar and wind are intermittent. They don't always provide us with power, so they have a rather random output. So we need to, if we're going to rely on these on a really large scale, we need to be able to store energy on quite a big scale. Store energy from when the wind is blowing or the sun is shining to when it's not. So what does that cost? So it's the cost of new generating capacity, the cost of grid enhancements, and of course the cost of energy storage capacity. And here's some calculations on that. So To phase out greenhouse gas emissions from electricity generation in the US by the middle of the century, we'd have to spend roughly $1 trillion. All the figures in that column are in trillions. There's all trillions here, it's 10 to the 12th. We'd spend roughly $1 trillion on generating capacity. We'd spend a tenth of a trillion on grid enhancement. That's a mere 100 billion. And then we'd spend, and this was actually the number that surprised me quite a lot when I did these calculations, we'd have to spend $2.2 trillion on energy storage. It turns out we need a lot of energy storage and it would be very expensive. That's a gross total there, if you add those things up, of $3.3 trillion. Just for standard, just by comparison, I mean, something that any economist knows, but many of you perhaps don't know, the US gross domestic product is around about $18 trillion a year, so $3 trillion is 1/6 of that. Now that's the gross total, but there are actually some savings to offset against that. So for example, if we replace coal and gas by wind and solar, we save fuel bills. We don't have to buy any fuels. How much fuel would we save if we, over the period from now to the middle of the century? We'd save roughly $1 trillion, 0.96 trillion, not $0.96 trillion to be exact. Also, it's the case that a lot of the power plants that are currently using coal, and some of those using gas, are obsolete already and will have to be replaced well before 2050. So it's not really appropriate to charge the cost of replacing those to the cost of avoiding climate change. They have to be replaced anyway. So we can net off those, and that would save us another roughly $1.06 trillion. So the net cost, as opposed to the gross cost, allowing for all these offsets, is the bottom line up here, which is roughly $1.25 trillion. What is that sort of in daily terms? Well, if you take the 33 years from now to 2050 and divide that number by 33, you get $37.6 billion, sorry, $37.6 billion a year. And that's the number I mentioned on my opening slide. And just for a sense of comparison again, in 2015, the US actually spent $42 billion on new electricity generating capacity. So that actually is less than we are currently spending on new generating capacity. So we're spending enough money as it is, we just have to spend it better. Stop building fossil fuel plants and use that money instead to build the aforementioned grid storage, and renewable energy sources. Now, in case you think this is all basically simple arithmetic, actually there's quite a lot of calculations of a fairly complicated type that lie behind this. Let me try to explain to you where those complications come in. They come in the first 3 lines up here. So the question there is, how much generating capacity do we need? How much do we have to improve the grid? In particular, how much storage capacity do we need? The issue that rises there, which is mildly complicated, is that the output of wind and solar power stations is essentially stochastic. We know on average what they'll produce, but we don't know how much they'll produce any particular day. So we have to sort of model the stochastic processes that generate the output of wind and solar power stations. And then we have to ask how much of these things do we need and how much storage capacity do we need to be, for example, 99% certain that we can meet demand on any given day. So it turns out to be a problem in statistical decision theory. And that's really where these 2 slides I skipped over came from. But incidentally, I didn't mention the footnote I got on this slide here, which says costs based on 2016 costs. So I costed these at what it would have cost to put these things in place in 2016. Again, as many of you probably know, costs have been falling quite rapidly over the last few years. Battery storage in particular is coming down a lot in price. So it's quite likely that going forward, these numbers will be an overstatement. That we can probably, I guess that given the way costs have been falling, it's likely that this will come in practice at under $1 trillion. Okay, let's switch quickly to transportation. So we have 2 forms of, our options here are basically to replace gasoline and diesel by electric vehicles, powered by batteries or by fuel cells. In air transport, there really isn't any alternative. It's unlikely that we will have battery-powered aircraft anywhere in the foreseeable future, I regret to say. It's possible that we can replace conventional jet fuel by biofuels, which has a lower climate change potential, but still not a totally satisfactory replacement. So we need to electrify cars. Cars produce about 34% of transport-related greenhouse gases. light trucks, which produce just under 30%, and heavy-duty vehicles, big trucks, which produce about a fifth. That's beginning to happen, but it's happening rather slowly. So most major manufacturers now offer battery electric vehicles. They haven't been adopted that quickly by consumers. There are issues to do with the range of these vehicles. There are issues to do with the costs. The costs have been dominated by battery costs, and batteries have been very expensive until now. And of course, the issue of charging and charge time, and the availability of charge locations and the time it takes to charge them. It's, I'm making a slightly speculative statement here, but it seems to me that the issue of range and cost will be overcome within a couple of years. You can now buy electric vehicles which will run 200 to 250 miles on a charge, and the costs of batteries are coming down quite significantly. A couple of years ago, batteries were costing $400 a kilowatt hour. Today, you can buy batteries, large-scale batteries, for $195 a kilowatt hour. They're expected to be down to about $100 a kilowatt hour within a few years. And that's one of the main elements in the cost element in electric vehicles. So there's a real chance that these vehicles will be affordable and reasonably priced within a few years. Now, vehicles last in this country typically about 15 years. So between now and the middle of the century, we've got roughly 2 vehicle generations left. If we want all of our vehicles to be electric vehicles by 2050, it means that by 2035, 15 years earlier, we have to be selling basically only electric vehicles, right? So what are the chances that by 2035, electric vehicles will constitute 100% of the new cars being sold? I think, frankly, your guess on that is as good as mine. Here's a number from McKinsey's. McKinsey's, the consulting firm, forecast that battery electric vehicles will be 50% of US light vehicle sales in 2030. That's sort of encouraging, but 50% by 2030 isn't 100% by 2035. And I think it's actually unlikely, without some very strong government incentives, that we will get to 100% electric vehicles by 2050. But we could get some significant fraction of the way there. Okay, let me just talk now about what's happening in other countries. I've focused so far exclusively on the US, but of course this is a global problem, and not much good are reducing our CO2 emissions unless other people do much the same. So this is a slide which I think is actually quite interesting. Look at the right-hand side of this. It shows you 21st of April 2017. And on that day, the United Kingdom generated all the electricity it needed for the first time ever without using any coal at all. On the 18th, it used coal to produce 800 megawatts. On the 19th, coal produced 600 megawatts. On the 20th, it produced 200 megawatts. And on the 21st, no coal at all was used. The United Kingdom plans to phase out the use of coal entirely within 2 to 3 years. And of course, the United Kingdom has been using coal solidly for generating power for hundreds of years at this point. That's an encouraging trend. Here's a global picture. So this talks about the last 10 years, from 26 to 2016. In that period, the US's use of renewable energy has gone from 3% to 9%, the UK from 2% to 25%, Germany from 9% to 29%, China from 6 to 10, Spain from 13 to 30, and so on. So other countries are making a lot of progress in moving from fossil fuels to renewable energy, more than we are. Here's another global picture. This shows you sort of global CO2 emissions up here. And the very interesting thing about that top left diagram is that if you look at it carefully, maybe just cast a little bit of faith here, you can see it's flattened off. So global emissions of CO2 have just flattened off in the last year or so. Why has that happened? Well, it's happened because if you look at this diagram here, you'll see that, for example, the European Union, that's the blue line there, emissions have actually been falling for about 20 years. Here in the US, emissions have actually been falling for the last roughly 10 years. And if you look at the top line there, even China, emissions have been falling for the last couple of years. So that's actually quite encouraging. Indian emissions, which are the ones at the bottom, growing quite rapidly, are still growing rapidly. But actually, India is also adopting an aggressive policy of installation of solar power right at the moment. What's behind this, you can see that in this diagram here. What's basically behind this is the drop in the use of coal. The United States has been moving away from coal quite rapidly. As I showed you, the United Kingdom is moving away from coal. Most industrial countries are moving away from coal. China is also, interestingly, moving away from coal, not primarily for reasons related to global warming, but primarily for reasons related to domestic pollution and the state of the air in the cities there. What do you think? The one problem with this diagram, as I'm showing here, is that this yellowish line is the use of oil and emissions from oil. That is growing rapidly. And that reflects the growth of private transportation in developing countries. As people get richer, they like to own cars. And cars are becoming the most rapidly growing source of CO2 emissions globally, unfortunately. Which makes the introduction of electric vehicles considerably more urgent. Okay, so let me just summarize. What I've told you so far is the US is making progress in reducing greenhouse gas emissions. Other countries are making progress too, perhaps doing somewhat more. We need to take more vigorous action on this front to meet the target of 2 degrees centigrade by 2050. The interesting thing is the cost is very low. And that's the point I emphasized early on. I'm going to go back to that point. The cost of essentially phasing out greenhouse gas emissions from power generation in the US for each of you in this room is $125 or a cup of Starbucks coffee every 10 days. And that's a very manageable cost, clearly. I'm mildly optimistic on the front prospect for climate change. It's very difficult to find optimists in this area these days. But I'm mildly optimistic about this in the sense that technology is there, the costs are manageable. It becomes really more of a political question rather than an economic question or a technological question. If you want a lot more detail about this, you can read my latest book. But thank you very much indeed for your attention.
We have time for a couple questions. Yes.
And in the New York Times seems to think that maybe the market will take care of things even without political will. What do you think of that?
Yeah, and Paul is not normally an optimist, is he? So the market is making progress. In the sense, everything I showed you in those diagrams there for the US in particular reflects to some degree what's happening in the marketplace. I mean, the drop in US emissions is substantially market-driven. What's forced US emissions down is the drop in the price of natural gas. The supply of natural gas has increased enormously because of fracking, which is not in general necessarily environmentally good news. But it has had the corollary effect of bringing down the price of gas, and gas is now undercutting coal massively. And that's why the coal industry is being forced out in the US. But I don't think the growth of wind and solar is really fully attributable to markets. I mean, wind and solar are now very competitive with fossil fuels. So, I mean, roughly the numbers are as follows. Coal costs to produce power from coal costs roughly 7 cents a kilowatt hour. Produce power from gas is about 5 cents a kilowatt hour. Wind and solar in the right locations, there's a caveat there, can be as little as 2.5 to 3 cents a kilowatt hour. So those are now competitive. But they've got there, not because of market forces, they got there primarily because of the renewable portfolio standards that about 30 states in the United States have adopted, which have forced utilities to adopt wind and solar and have brought us a long way down the learning curve and generated economies of scale which have brought the costs down. So it may be that going forward, those are self-sustaining and we don't really need heavy policy support, but we wouldn't have got where we are without that. And I think we need something similar in the area of transportation.
So you presented an argument more or less as a continuum, a continuous argument over the time. What happens to the cost and practicality if you don't invest at the level that you've discussed, say, as just a randomly picked example for 4 years or 8 years?
Yes, I can see exactly where you're coming from. You have to invest harder later on.
Does it change geometrically as you go onwards if you don't invest early?
Yeah. Well, so, I mean, if thinking a little bit into why you're asking this question, one of the fortunate things, actually, is that there is no effective federal policy on climate change. All of the policies in this country on climate change are basically state-level policies. Trump is repealing the Obama Clean Power Plan, but the Obama Clean Power Plan, unfortunately, never came into effect because it was frozen by the courts as soon as it was promulgated. So Trump is repealing something which has never actually operated, which is pretty typical, I guess. As I said just now in answer to the other gentleman, the really powerful levers in this country have been the state-level renewable portfolio standards, the kind of legislation at the state level which says, In the case of California, for example, 50% of all power has to come from renewable sources by 2025 or whatever it is. In New York State, we have a similar legislation, and that's been very powerful in driving the adoption of renewable technologies. And that's something which, fortunately, is not controllable by the federal government. Although, I mean, there was a speech by that guy who's Secretary of the State for Energy, I forget his name now, Perry, the other day, which made me think that he was beginning to see if he could possibly get his hands on this and repeal some of these renewable portfolio standards. But it's not something it's easy for him to do, apparently.
Okay,
Thank you.
Yeah,
last
Oliver.
question.
Two very small questions. First of all, your numbers were all presented as absolutely certain. There were no standard errors, confidence intervals, which
Right.
maybe it would be good to know a little bit about.
Yeah.
The second thing is, I'm sure something that was occurring to everybody here, which is if you're right that the cost is so low, why is it politically so difficult to get something done?
Yeah, two great questions. Okay. There is obviously a large margin of error around those results. I should emphasize these are orders of magnitude rather than precise numbers. As I said, this is a problem in statistical decision theory. It's based on sort of models of the distribution of output from wind and solar farms. And we don't have as much data as we'd like on that. So those estimates of those distributions are rather poor, frankly. But it's a first estimate, and I don't think it could be wrong by 20 or 30%, but that wouldn't radically change the story, I think. That's an important point there. Now, why is it so politically different? Yeah, the reason why it's so politically difficult, I think, is the following. That what we're talking about here is basically wiping out the oil and gas industry, because most oil anyway goes into transportation, and most gas goes into power generation. So we're talking about essentially shrinking the oil and gas industry massively, and we're talking about radically restructuring the automobile industry, whose intellectual property is all built around internal combustion engines. For much of the 20th century, oil, gas, and automobiles were the backbone of the US economy. Those are very politically powerful industries, very rich industries, and they employ, historically, it's employed an awful lot of people. So they have leverage politically, which I think is out of proportion to their current and future economic importance.
First, I want to thank all the speakers. This was the best session.